Okay, Nelson Pass.
We're amplified, that's great. There's room up front. Contrary to rumor, I don't spit on the audience. And so...
I'll take advantage of that.
Okay. It's a pleasure to be here. Isn't this where the very first set of
very important point. Yeah.
talks, and I mean this was the podium, or this was the place. And what's this, number 11? Or
I'm not sure we had a podium back then.
yeah, no, we didn't. We didn't. We had tables and stuff in the back. As always, I've put together a talk which is its formative stages are simply a series of pictures of stuff that I'm working on, which usually, can be turned into something that I can string together with some vocal help. And this one here is selected topics on FET push-pull output stages. I've been doing this for almost 50 years, and that's building amplifiers, by the way, and don't look for anything else. The thing that almost always has interested me the most about amplification is the output stage. It's where the power is. It's where the rubber meets the road for an amplifier, and it's typically the place where most of the action, when you're really trying to get high quality, it's where most of the focus ends up having to be, partly because it has to dissipate lots of energy. The characteristics of it are such that it's got to be able to dish out a lot of current. It is directly talking to the loudspeaker. Now, front ends and other stages are certainly very important, but to me, output stages are the most fun. And what I've been doing for a long time, and more recently even focused on even more, is just building output stages without any other circuitry and listening to them. And then when I've developed something that's interesting, then I can consider whether it gets added to an amplifier that has a front end and other pieces and so on. But the output stage, to me, is the most interesting part. There are some subtleties to it that I would like to share with you, and there's also some interesting little things that are perhaps not commonly thought of, but the idea here fundamentally is for you guys to build your own stuff, and you probably could use a few tips in regards to some of this, but the other thing is this is where the most fun is, and I'm trying to encourage you to tackle some of these kinds of projects, and yet they can be very, very simple, which is the best part of all. In all of the years that I've been doing projects, I have found that the ones that were the most popular were the ones where it really was the simplest, and interestingly, it didn't matter how much big hardware was required. In other words, one of the most popular of all was called the Son of Zen, which was an output stage that consisted of just 2 transistors and nothing else, but it required huge resistors. I mean big, huge resistors, big monster power supplies, giant heat sinks, but it only had these 2 transistors. I talked to a lot of people who built it, and they went, well, I can saw, I can mill, I can drill, I can weld, I can do all those things, but I'm afraid of those little 3-legged beasties. And so the reason that most people tackled that, I think, was that it had a real low barrier to entry. There were only 2 parts for transistors in it, and they only cost a couple of bucks. You could blow them up, and you weren't going to be in any real big trouble. So that's what I want to talk about. I want to talk about specifically push-pull output stages, FET push-pull output stages, and also the fact that I'm also, and it didn't say so here, they're all followers. If I can have the slide. Okay, this is like your basic output stage for FETs. It's got the most common parts. Bob Cordell will certainly recognize this. I've seen this sort of configuration often enough in his stuff. And what you see, which I can barely see, what you see are two transistors. At the top, you've got, in this case, it's called an IRFP 240. It's like gumdrops. I mean, in quantity, they're 80 cents. And on the bottom, you have another one called an IRFP 9240. Costs a little bit more. They are two different kinds of parts, but they are similar in another way. The one on top is an N-channel part. The one on the bottom is a P-channel part. And they're very similar, but they are mirror images of each other. You have, on these parts, you see the little part where it comes off on the left. There's a pin, there's a wire coming in from the middle. Those are known as the gate. I should have labeled these. And at the top, on the rail voltages, where you see plus 23 and on the minus 23, those pins are called the drains. And the pins that connect together, those are called the sources. This is a follower system. If you set it up properly, any voltage that you put at the input is going to appear again at the output without any voltage gain, but with lots and lots of current gain, so that the input impedance on this is very, very high. I mean, we could be talking megohms under some circumstances, and the output impedance can be quite low, well under an ohm. So if you've got a signal that you wish to simply current amplify, this is a perfectly fine way to do it. This is what a lot of output stages look like. It certainly looks like the ones that I usually do. And there's a couple of subtleties here. One is that, well, let me explain very quickly. On an N-channel device, you see on the left the gate pin. That's a control pin. The amount of current going through the FET is a function of the voltage between that control pin and the pin down below it, the source. As you vary the voltage between the gate and the source, you vary the amount of current that will flow through the part. And in this case, if I have a positive voltage going to the gate of that N-channel FET, it will put out a positive voltage at the source and drive the loudspeaker with a positive voltage. And same thing with the P channel. If I give it a negative signal, it will be very happy to deliver a negative signal at the output. They don't do so coming out of the gate. They require a little bit of bias, as it's referred to, because it actually, the following action in this case, when the current starts to be conducted, occurs at a voltage, in the case of the N channel, at about 4 volts or so. In fact, a little bit less than 4 volts. But you won't even turn on until you give it at least that, and then it'll start following. And on the P channel, it won't turn on or conduct any current until the voltage hits a certain level to start with. In this case, again, about maybe minus 4 volts. And you're familiar with probably, or you hear a lot of, class of operation, class B, class AB, class A. All of those things revolve around how this has been set up. If the voltages that are used to bias this, the bias voltages, you see a voltage source on top that says 4.4 volts. And you see over here a voltage source that I've provided for these parts at minus 4.5 volts. That's enough voltage on those gates to get these parts to conduct current just sitting there. If they were lower voltages, it would conduct less current, and if they were much lower voltages, it would stop conducting and would maybe just barely conduct. If you're running very low voltages and very low current running, just sitting there running through the stages, that's a class B, wherein if you increase that voltage and then the current a bit, then it becomes class AB, and as you crank it up, it starts moving into what's known as class A. In this case, this is a class A circuit. It could be operated in any of those 3 ways just by adjusting those voltages. But you see here, a little note, this one is set up at 1.3 amps bias. I set it at 1.3 amps bias and plus and minus 23 volts because that's my standard 1st watt power supply, and it results in the heat dissipation levels that fits on one of the heat sinks of a 1st watt amplifier, of which I bought the parts for $2,000 once upon a time. So I tend to design almost everything around these sorts of voltages because I've got tons of those transformers, tons of those heat sinks, tons of those transistors, and so on. So, but the other thing that it's going to give us here is that when I go to compare some different types of arrangements and so on, a lot of the conditions are going to be identical because all these amplifiers are going to be biased at 1.3 amps, and almost all of them are going to be running at plus minus 23 volts. And all of them are going to be followers, and all of them are going to be kind of like this. In fact, there'll be different parts, and there will be maybe some different voltages being employed to bias them up to those currents. But this is the standard, shall we say, paradigm that we're going to employ in this talk. So here's this part, and here's this circuit. This would be a real amplifier. I've got plenty of examples of exactly this, and I listen to them. You have to listen to them with something that can deliver real voltage, because I don't have any voltage gain. So if you want to, if you want to put out a waveform that peaks out at plus and minus 20 volts or so, given the supplies that we've got, it's not going to go a lot higher, then you need a source preamp that can swing plus minus 20 volts and the gain to get you there. But that's not such a big problem. In my case, I have such circuits laying around. In fact, at Past Labs, we build preamps that do that. And the reason that we do is that I told the designers that I want this thing to be able to swing that, because I like to listen to these stages by themselves, evaluate them for performance, and worry about what kind of thing it's going to be enclosed in later, or whether it's going to have feedback on it or not, and so on and so forth. I like to listen to the raw stages. I like to evaluate the performance of the raw stages with instruments and measure the distortion and so on as a piece. And rather than trying to worry about what the whole amplifier is going to be when I'm all done, I'd like to be assured personally that each, maybe a little bit less gain, I'd like to be assured that each piece that goes into the amplifier has got the kind of qualities I'm looking for. And I'm looking for measurements, but I'm also looking for sound. And to me, the sound is an important thing. And it's there, and it really comes to the fore if you haven't put feedback around it or done a lot of other things. In other words, it's a pretty raw circuit. Can I have the next one? So, this is a very nice circuit, but it's got some issues you got to deal with. One, the bias current on this, that 1.3 amps that I ran through that stage, okay, is temperature dependent. Okay, so you imagine this, that I've got this circuit, the plus and the minus, the N and P channels, and they're all set up, and I'm going to drive something, and I apply the voltage, and I crank up those bias voltages to get it at 1.3 amps, and I go, okay, we're great. At 25 degrees centigrade on the sink, we're great. A little bit later, when that heat sink has warmed up, because we're biasing that system at approximately 60 watts or so, that's what it's heating up at, which is 1.3 amps times 46 volts. You find that, gee, my bias seems to have drifted on up. In fact, as it reaches, 50 degrees centigrade? Yeah. When the heat sink is reaching 50 degrees centigrade and I go to measure it, I'm going to be about 1.8 amps. It's gone up 40%. That could be a real cause for concern. One of the nicest things about FETs is that you can get FETs that don't drift so much. These aren't the best examples of it. And the other end of it is they don't drift anywhere near as bad as bipolars. With bipolar transistors, if we had waited around for that 50 degrees, probably smoke would be coming out at that point, because they really go to town and require more attention to that factor. The FETs, however, still require some. And if there isn't enough heat sinking, part of this is how much heat sinking you got. If you've got lots of heat sinking, the drift won't be as high. But if you don't have all that much heat sinking, you could see this thing just kind of start running away with it. It might not run away to the moon, but it might break on the other hand. So you have to address this. Can I have the next one? Let's see. Oh, I believe I covered this before. You know what? Oh, that's okay. Just because it's text, I'm getting confused. The MOSFETs have that voltage that I was talking about. It's called V sub GS, which means the voltage between the gate and the source. That's the control voltage that tells you how much current is to go through the MOSFET as a concept. If we had perfect ideal MOSFETs, then we would just set it and we'd be all done. But we already know that they drift. Let's see. Also, another issue that comes to fore is that if you're sometimes paralleling these devices up, you have to match them, because I can't have a MOSFET that has a 1 volt VGS to go to 1 amp and another one over here that goes to 1 amp at a half volt, because then when I go to some figure bigger than a half a volt, the FET will be going and taking all of the current. And so you don't want to have FETs that are paralleled up. This is true of bipolar transistors also, even worse. And you have to match the FETs for VGS at a given temperature and current through the FET. This is not so hard to do. I did write an article on that subject, but you do have to do that. And the other thing that you find out, though, is that even if you do match them, as the temperature goes up, they will drift apart from each other, okay? And so it becomes something that you have to consider if you're building these kinds of circuits, that you'll set them at some bias point and they'll be running at, say, 60 watts, and you come back a little later and, oh my gosh, they're at 100 watts, and you burn your hand on something, if you're lucky, and if smoke comes out if you're not. The other thing is that normally we don't talk in terms of telling people that they want to match their N and P transistors all that much. When I talk about paralleling devices, and I need VGS matching, I'm talking about devices which are of like kind, 2 N channels, 3 N channels. At Past Labs, we sometimes, well, I have amplifiers where we have 9 parallel devices. We have to really quite careful matching the VGS on these. And but as a rule, we don't bother to try to match the VGS figures between the P and the N channels, because A, they're different enough kinds of parts that isn't necessarily going to buy you what you want, and the other is that it's very difficult to do. If you have a population of parts and you've got a whole bunch of them that are 4 volt, and then the P channels have to go with them, and there's tons of those at 3.5 volt, you're going to find very few matches. So you live without. However, that does impact the distortion of such an amplifier, okay? And so as a concept, you would try to do some kind of matching for the parts. The issue that you'll run into is that of, well, I'll tell you what, I'll tell you a little more about that in a moment. But in a case of where the parts are ideal, what we call square law devices, where the equation for the current that goes through the part is a function of the square of the VGS. If you put those together, P and N as followers, and everything else is ideal, the distortion exactly cancels to the extent that the parts are matched. They're never that well matched, so we won't get too excited about it. But I wanted to bring that point up, is that at least in theory you can really go to town with this and end up with something as a concept that has no distortion at all. Not that you'll experience that. Can I? But the thing about the thing with P and N and having that cancellation of characteristics through the square law function that they try to operate through is that it makes for a very attractive thing to work with when you're trying to get very low distortion figures, and when you're working with this, it's a case of suppressing the differences between the parts as much as possible. And if you can do it absolutely right, the distortion literally is mathematically 0, but then that's the perfect part. This is the circuit I showed you before, and I show it to you again so I can show you that circuit by contrast. There's only one difference between them. There are resistors inserted between the sources of each transistor and the output. They are of relatively low value, in this case 0.47 ohm, a little bit less than a half ohm. What they do is they equalize, they do two things. One is they tend to equalize out the characteristic of the part, so that the fact that your P and your N channels are different they're made a little more similar, and the distortion can be made to go down. The other thing that it does, which is what people are usually really after, is to keep the thermal drift at bay. The amount of resistance in this case is roughly equal to what we think of as the inverse of the transconductance of the parts themselves, so that if the transconductance of a part is, say, 2, which means for every half volt of VGS you get an amp, that is the inverse of the roughly half amp of the resistor that I've chosen. What we do is we essentially have the contribution of the idiosyncrasies of the FET. We could make these values higher. You can make them anywhere you want, but at some point you start seeing more drawbacks. If you're trying to drive an 8 ohm load and you make those resistors 20 ohms, your efficiency figure is going to drop right down into nothing. This is a very good compromise value. There are people who use a little higher values. There are people who use lower. There are people who use none at all. Now, the thing about the none at all, oh, by the way, and this is called degeneration, okay? This is actually what you might call the other form of feedback. What you have done is by inserting resistance in here is you have lowered the gain of the devices by adding a resistive element to its equation. And you have stabilized the bias. You have tended to equalize the characteristics of the P and the N channel so that they are more symmetric. And, well, actually, that's pretty much enough right there. If you go to work with these, and suppose you just ignore whatever small amount of variations and distortions you're going to see from between the P and the N. In fact, if they're perfectly matched, then there's no problem at all. But if you work with this and you settle for the fact that the bias is going to go up 40%, in many cases, you can get away with that. You can't get away with that kind of thing with bipolar transistors because they run away a lot faster. Depending on the type of FET, you might not have to bother with it at all. There are FETs out there which have a 0 coefficient or close enough to it that you can set them at 1.3 amps cold and come back and there'll be somewhere pretty close to that figure. Those are known as laterals. Or in the case of MOSFETs, if you're running enough current through them, if you're running really high amounts of current, they'll find a 0 coefficient point where the temperature no longer particularly matters either, and you can play that same game. If you are a fearless amplifier builder like me and the rest of you who care to be, you can try this for yourself, fire that up at 1.3 amps cold, let it drift up, reset the bias, and see where it gets you. At some point, it will probably stabilize, and the bigger your heatsink is, the more likely it is to do that, so that you can, in fact, operate without those resistors. Now, you ask the question, why wouldn't I just want to have the resistors, period? In other words, why not just take the degeneration out? Can I have the next? Well, degeneration is the other negative feedback. People argue about that on DIY audio, particularly often in the lounge section. They really get into discussions about negative feedback, and one of the favorite points that gets made is, well, but you say that your amplifier has no feedback, but you're degenerating some of your parts with these resistors, therefore it has some form of feedback. It's known, in the textbooks, it's literally referred to as the other form of feedback. Well, that's bad. That's awful, isn't it? It certainly makes it difficult to argue this point, which is what the lounge is all about. But it is a form of feedback, and you have to kind of recognize that that's really the case. The other is that degeneration helps with the issues by improving the matching and improving the temperature stability. And by virtue of improving the matching a bit, it also lowers the overall distortion numbers. Can I have the next slide? Okay. Here's that circuit with and without the resistors. Okay, I worked it up, ran the distortion curves. The one on top is the one without the resistors. Okay, the one on the bottom is the one with those 0.47 ohm degenerating resistors. And here we are. This goes up to 20 watts because my audio precision can deliver 13.3 volts and no more. Well, that's 20 watts as far as this cares. So you'll see all my curves stopping at 20 watts because these are followers. They don't add voltage. The audio precision only gives you 13.3 volts. And so all the curves you're going to see here go to 20 watts with maybe one exception. But you got two curves. The top one is without degeneration. The bottom one is with. And what you look at is, look at a watt, for example. It's half the distortion by virtue of those. And it also is the same proportion in which we have degenerated that part, because those parts were, if you looked at the internal working of the FET, it would be almost as if there was a half ohm inside of there. In this case, having added a half ohm, we lower its apparent gain by a factor of 2, but we have the distortion to go with that. Can I have the next one? Now I'm getting rolling. I know what I'm talking about finally. Yeah. Okay. The downsides. Well, there is a downside. Three things. One is that it does raise the spectral complexity of the distortion curve a bit. In other words, if you've got an undegenerated circuit that's got this really cute, nice, clean-looking second harmonic sine wave for distortion, if you degenerate that, you're going to start seeing some higher harmonics come in. The thing isn't going to look quite as pure, although the distortion will be lower because the harmonic itself tends to be suppressed, but other things rise to the fore and raise their ugly little heads. And as audiophiles, we all know that higher order harmonics are not as good as lower order harmonics. That's kind of true, all other things being equal. It raises the output impedance. That circuit that I showed you at 1.3 amps with the N's and the P's and everything, that has a damping factor of about 50 or so. It's quite good all by its little lonesome. You would have to consider whether or not you would need more damping factor than that anyways. If I put in the degenerating resistors, it drops by a factor of half, just like other things have dropped by half. So now your damping factor is like mid-20s. The other thing is, it lowers the size of the Class A envelope. And this will take a little explaining. Next slide. Okay. Here is a fast Fourier transform, an FFT, of the distortion harmonics on, in this case, that same circuit with no degeneration. And what you see, this is decibels of distortion off on the left-hand side. It's minus 60. Minus 80 is 0.01%, okay? Minus 100 is 0.001%. Is that right? Yeah. And down here is 1 part per million at 120 dB. These are really, really low distortion figures here. This one here is 0.0, little. I mean, this thing came in at about 0.02, 0.03%. But the 80 figure, that's for the 0.01% number. You see the second? You see the third? The third's down about 15 dB or so below that. And then you've got some fourth, fifth, sixth, and seventh sitting down here below the 1 part per million in most of them, or just slightly above it. This is how that circuit looks if you're running it, in this case, at 10 watts into 8 ohms. Next slide, please. And this is what the distortion looks like without the degeneration. And you see that the green part, which is the distortion as compared with the original signal, this is a very, very small portion of this, but it gives you a sense of what the waveform looks like. This is second harmonic. There are 2 humps for every hump on the distortion, that for every hump that you see in the sine wave, so that it's at double the frequency. But if you look at it, you go, yeah, I at least recognize what appears to be mostly a sine wave. It's fairly clean looking. There aren't any nasty things sticking out of the sides or, you know, gross asymmetries. It is a pretty clean second harmonic, but we saw that from the previous slide, whereas mostly second, it was a little bit of third. Please. Now I degenerate this. Okay, I put in the 0.47s. What have I got? Well, my second went down quite a bit. Well, we kind of knew we've created some symmetry here, but if and I'm not going to go back to do this, but I'm going to tell you right off the top, our third went up a bit. Okay, in fact, the third went up to where they're just about equal. My fourth, fifth, sixth, seventh, eighth, and ninth have all notched up a little bit. In fact, some of them have made new appearances. Keep in mind that these are not big dramatic things. We are talking about 1 part per million at this level. What is it? At 100. Well, this is at 100. It's 0.001%. Am I right? Yeah, I'm right. I keep looking at Bob because he'll, Anyways, so you got some more high order harmonics. Everybody goes, oh, well, that's really terrible. Well, but they're really at low levels. I mean, it's not a reason to get excited. On the other hand, you want to understand these phenomena, that you do these things. These are the things that kind of crop up. Whether you want to get excited about it or not, myself, I don't lose any real sleep over it. I would rather have an amplifier that doesn't blow up or have other issues solved sometimes. But if I can build amplifiers that don't require degeneration, well, they're a little bit better. Or maybe not. A little second harmonic doesn't hurt anybody, and even less third won't really hurt you. I have made plenty of money with amplifiers that had second harmonic distortion, and all sorts of people say, well, these sound really good. And I could get into that, but another time perhaps. Next slide, please. Oh, this is the part where you can ask questions. Yes?
So when do you lose sleep? When do you lose sleep on these numbers?
Oh. I lose sleep only on whether people are buying something or not. So if they really like something, then I sleep really well. And if they don't like it, actually I still sleep, but I move on to the next one.
Maybe rephrasing it, at what levels do you start to notice audibly?
Well, my rule is that somewhere I've noticed is somewhere above 0.01%, and
that does depend on the order of the harmonic. Do you hear the ones quicker?
Oh, I see. It's really tough. It's really tough. It's tough to make experiments that are that good. In general, I know people. I have known people. One of them is a business partner of mine from. Well, I knew him for 40 years, but he's deceased recently. He was the sharpest ears I ever ran into. He could hear the difference between that circuit, those two circuits that I showed you, and in a blind test. Now, how this test was conducted will be of interest to you because it wasn't with me standing over him with a switcher. At First Watt, I've told you, I got thousands of these chassis, and so I can build duplicate-looking amplifiers. In fact, when you look inside, you still don't see any difference between them, and nor would this person look inside because that's not part of the test. And but I could, and this test has actually occurred. That particular one, Joe, I put 2 amplifiers in the back of your car, and take them home, and let me know what you think about it. 3-4 days, a week later, Joe would come back to me and say, this one is really good, this is good, and this one, not so much. And he would have put labels on them so that we could tell which one is which, because there were no identifying marks. And as you saw, the circuits were really, really nearly identical. And they measured awfully close. Well, the differences that we're talking about here are really slight. He could hear that stuff. I'm not so much. I mean, sometimes I go, yeah, I think I hear that. Maybe I like that one better. But he was reasonably unequivocal, and he was right about 90% of the time. So we learned over a period of time that degeneration was something that at least he could hear, and so we take this as an article of faith that there are other people. I've met some other extremely sharp listeners also. They're real hard to come by, but I have seen them. So in terms of where this starts counting, I don't know. Myself, I tend to say that when we get down below 0.01%, I don't hear it anymore. And there are people who are out there plumbing for 1 part per million or better figures, possibly on the assumption that people are hearing something that we're not measuring, and so we need to improve our measurements, or maybe we need a new test, and so on. Honestly, I tend to think that the failure in these cases to correlate these measurements against what people hear is more of a failure of interpretation than that of the quality of our measurements, or that, the whole notion that we can actually measure what people are going to hear is awfully tough, because the brain is a very complicated thing and doesn't work halfway where we would like to see it. The story goes about the drunk crawling around under a street lamp at night and searching for something, and a cop comes up and says, "Well, what are you doing?" He goes, "I'm looking for my keys." And the cop says, "Well, did you lose them here?" And he goes, "No, I lost them up the street, but the light is so much better over here." Now, we have the ability to measure all sorts of things really well, okay? But maybe we're not measuring quite the right things. But I think it's just a case of interpretation. The ear is not a microphone, the brain doesn't have a tape recorder, and so on. So there's room here for subjective judgment. The presumption has always been that if we do make these things perfect, well, then we're done. After all, if there is no difference, you're all set. That opens a whole different can of worms, which is, this is the entertainment business. As my deceased partner Joe would have said, it's not dialysis. And so I personally don't have a problem having products that have some personality to them. That doesn't mean that I add lots of distortion and I go, ha ha. Well, actually, I've done it a couple of times. But as a rule, I don't. I like to get the numbers down around 0.1 or something like that. Get it down below 0.1%, unless I have a really good excuse. Sometimes I do it just because the circuit is so cool, I will put up with it. But that's entertainment. But I think offhand, I don't lay awake at night worrying about getting that last iota down below those numbers. 0.01 is about as low as I think. Can I have... Oh, wait a minute. Any other questions? We're still in question zone. Yes?
I think I see how this works now, but how does DC across the speaker outputs happen? How do you get DC across the outputs? How do you prevent that?
How do you get... I'm sorry, I'm being... what?
I apologize.
That's right.
Well, how does the DC across the outputs happen? How do you prevent that?
Oh, well, you saw how I had a plus bias voltage and a minus bias. If both those are adjusted just right, then there's no DC at the output. Because the input is assumed to be at 0, and so all I do is I set them independently. In fact, I routinely have circuits where this is exactly what I got. I have two bias circuits, and this one is set, and that's one set, and their bias is right, but the offset's wrong. So then I tweak one, and I raise the other one, and it's an iterative process. Something that DIYers can do, by the way. You guys have all the time in the world to sit at a bench and let it warm up and move it around a little bit and get it as close as you want. Manufacturers have no time for this sort of stuff at all. It's like down the line. That's one advantage that DIYers have, is that you can take simpler circuits, simpler concepts, and still deliver really great amplifiers, because you don't have to do so. They're not on a production line. They don't have to be ready instantly. You can warm them up. You can play all the games that you might until you're satisfied with whatever you got. So I've got lots of circuits. The VFED amp has got 4 pots on it that have to be done in rotation, because each one affects the others. And what you don't do ever is set the pot value to the value of the thing that you're measuring that you want. You move halfway there or a third of the way there. Then you go in rotation around all 4 pots, measuring the thing that goes with them until they're all in agreement. But we do this incrementally. And we actually had a guy on the forums at DIY Audio who didn't do that, and he never could get it to 0 out. And we said, no, back off. Just go, little small changes and run rotation through all the adjustments, because in many cases, and that would have been one, they affect each other a bit.
Does that drift over time, or is it just thermal dependent?
Yeah, they drift over time. Okay. The good news is that most of the time they start up cold in good shape, and when they warm up, they drift into the spot where you want them. I mean, where I don't actually work there anymore. I work elsewhere. But at Past Labs, we have a place where we warm them up, and we set them, and then they warm them up on the bench for a little bit, and they tweak them in, then they burn them in, and then after a couple of days they come back and they tweak them again, and then they let it sit there for a couple hours, and then they tweak it one last time, because it kind of does that. And then the customer goes, you know, it sounds so much better after an hour. We go, well, it says so in the manual. You know, we do all of our adjustments at temperature, and it's good, you know. But the other thing too is we just run real high biases. So as a rule, it can drift a little bit. It doesn't change the sound that much when you're running a lot of bias. Why don't I go ahead? Okay, I was talking about biasing, and toward that end I wanted to talk, I was also discussing the Class A envelope as being affected by the degeneration of the output stage. Here we are, this is what in a Class AB amplifier, and a class, kind of like a Class B also, looks like if you're looking at the currents simultaneously of the N channel and the P channel. You can see that between them they form a sine wave, but they're like the guys in a relay race. You've got the P channels handling all the negative voltage and current, and then it gets up toward the zero and it hands it off to the N channel device, which is in red, and it runs with it for a lap, and then so the signal is like a baton, and it's being passed between two runners in a relay race. Now, the amount of bias, the amount of idling current that you run through an output stage has a real effect on the quality of the transition between the two halves. And to go back to the relay race analogy, in a real relay race, well, imagine a relay race where the guy running up with the baton and it's time to hand it over to the other guy stops dead and goes, oh, here you go, and then the other guy starts running. Well, they will lose a lot of races. That's what a Class B output stage is kind of like. One of them stops dead, and the other one has to get going. In a Class AB, you throw some current through there, and you clean up that action a lot, what they call the crossover distortion. And that would be roughly equivalent to having the two runners in a relay. And like in real life, the guy who is going to receive the baton starts running a bit before he gets the baton. He's already in motion, and so the transition has occurred with both of them sharing the baton, okay? And so, needless to say, that's how real relay races are run. Class A takes that one slightly crazed step farther, and if it were the relay race, both guys would run around the track holding the baton at all times. Okay, there's not much term. One gets to hold it a little closer for a while, and then the other one, but they never let go of it. So, but I wanted you to get the idea of the fact that we're running this kind of alternate relay scenario between the two halves of this output stage. And the reason that we have two halves in push-pull is it does really give us low distortion numbers. It also is extremely much more efficient than the alternative, which is single-ended. There's a lot of people who love single-ended amps. I'm one of them, but we're not talking about them today. Next slide, please. This is our, and we're looking at the current through the N-channel device of the previous circuit. This is the one without the degeneration, so it was the first one that you saw. And what I've done is I've gone in and I'm actually looking at the amount of current through a very small resistor in the power supply that's going through the positive transistor as it goes through this power waveform. The power waveform in this case is 40 watts into 4 ohms, which for this circuit is, it's short of clipping, but it's like we're cooking here, 40 watts into 4 ohms. If we look at this, you see a 0 mark. That's the point where that transistor, the N-channel transistor, actually ceases to conduct current. And in this case, we have a calibrated division here of 400 milliamps per vertical division. So for instance, the bottom trace, where the N-channel device is at the minimum amount of current that it's conducting, and the P-channel is almost doing all the work. But this guy is still turned on. He's just got his finger on the baton, as it were. He is still conducting 400 milliamps of current. Well, under those circumstances, he's actually still got what we'd call, I think Bob would probably call, a reasonably substantial percentage of the action. Now, in point of fact, the other guy is still doing most of the work, but you'll notice that the waveform still looks a lot like a sine wave. If we jump back to, can we just jump back one? On this one, it doesn't look that much like a sine wave. Look at that red trace, okay? That's class A, B, even class B. You'll notice it's flattened out, it's shut down. And we can go forward again. Thanks. Oh, there we are again. Okay, so it's actually holding on some of this. And by the way, this is a fair amount of juice. The peak current that's being delivered on this thing at 40 watts is about 3.17 amps to the load. And there's still enough left over to keep the other half that's not doing nearly as much work in conduction and show, as we say, making a contribution to this. Now, this is a function of what we call the square law effect. The VGS relationship to the current through the transistor is a square effect. If I double that voltage, you get 4 times the current, at least in the ideal case. None of these things are actually ideal. But it's a good start. It's a good first order approximation. Now, with square law, with devices where it was totally degenerated, let's imagine that the square law thing didn't happen at all and that there was really large value resistors between the sources, like we saw the 0.47s, but go even to higher figures, we would discover that the peak output current in class A would be twice the bias current, or 2.6 amps. Because, and we haven't fallen out of this thing yet. We still got some margin left. But at this point, we're putting out 3.17 amps. We're putting out more than twice. We are operating at what we could think of as a slightly expanded Class A envelope, just because of the square law effect. So that if we had in the, again, ideal cases, if you had the usual thinking is that, oh, I've got a class A amplifier, it's idling at 1 amp, let's say 50 watts, for example, and it'll leave class A when 1/2 of it is doing 2 amps. That gives you this basic 2-to-1 ratio of dissipation versus rated output in class A. The square law grants you that little extra margin that you would always like to have on a sunny day. Instead of twice as much, this one is, I don't know, 2 point something more. It turns out that if you have perfectly great square law devices, if they literally are square law and perfect, it doubles. You got a 2 amp, if you had a 1 amp bias, you can have a 4 amp output before the side shuts off. You're not going to see that typically unless there's some other fault. But the point here is that square law, the square law effect doesn't necessarily limit you to exactly twice the bias current for for class A output. Now, take a note of where this is cut off, because it's at 400 milliamps, because the next slide is with the degenerating resistors in, and we see that in fact that figure has gone down to about, well, once again, half that much. This output stage will leave class A at a lower output wattage than one which has not been degenerated. So that there is a slight disadvantage going on here. Now, it's up to you to decide whether that's important to you or not. But I know that if you really work this angle, you can actually get the thing to go out quite a bit farther. And you can, I have seen circuits where I was able to nearly double the class A output rating of an amplifier for a given bias. Now that comes to the issue, all right, now what's really class A? What are we supposed to be doing here? Well, the old rule that it's got to be, twice the dissipation for X amount of power wasn't a particularly good rule anyways, because things are never that good. But the other end of it is, it's still got forward bias, and it's being done without any tricks. Nobody's adjusting the bias. There are no special circuits. The FETs do this all just by themselves. It it behooves us at some point as an industry, if we're going to argue about what's really Class A and what's not, probably to decide where the limit is. Because I've got some cases where you can throw tons of current off the other side and this thing flattens out, but oh my gosh, there's still 2 or 3 milliamps worth of current going through there. Why, it's Class A. Well, probably not. One way of looking at it is, how much is it flattened out? Well, it's not flattened out very much, so I would say, yeah, that's still Class A. If we go back to one of the earlier ones where you see it as flattened out like that, and even though that there is some current maybe still going through it, I wouldn't call that so much Class A. It tends to be referred to as non-switching for people who are trying to put a finer point on it. The virtue of non-switching isn't so much the value that it brings to the table for FETs, but possibly for bipolars, where sometimes the speed is a little more of an issue in turn on and turn off. Can I have the next? Oh, okay, time for more questions. Okay.
Well, I apologize, I'm not an expert on looking at just reading circuits, but what you've shown, they look very pleasing to the eye, and the fact that they look very symmetrical. Is that just the nature of the push-pull output, or did you make them that way on purpose?
No, that's the nature of the beast. We're looking at raw curves here. We're looking at no magic on my part, except that I know how to hook the stuff up.
Okay, so you need a lot of good symmetry, it looks like, on both.
Ideally, the more symmetry you can get, you can exploit that to get nice looking curves. But even asymmetric, even parts that aren't matched that well, now they tend to do this. Okay, it's subtle.
Is the 0.47 ohm source degeneration that you normally use chosen as a convenient number because it's enough resistance to make your parts match? Or is this one of those where you get better matched parts, you can use less resistance? Or is it just that you bought 100,000 resistors and you haven't used them yet?
All three.
That's what I
You go to DigiKey and you look at the Panasonic resistors, the lowest value they make is 0.47.
So obviously AB has a lot of advantages over A practically, but do you find that for holding things constant, that A will always sound better? And so AB's, practical, but...
I have actually heard push-pull Class A amplifiers that did not sound as good as an AB example. But I presume that there was some other issue. Okay, I take it as an article of faith that Class A, all other things being equal, that we haven't screwed up somewhere. Yeah, no, Class A has got a lower distortion character. And it has better damping factor. Those higher currents give you higher transconductance on the parts. The damping factor gets better. All the things are better. So, no, I mean, the problem with Class A is it takes big hardware and it burns energy. Something that DIYers can afford to do. Manufacturers doing mass volume, there's